These notes are about sequences and patterns. Let's have a definition first of what a sequence is. You probably already know. A sequence is just an ordered list of numbers defined by some rule or pattern, usually. So it's basically just a list of numbers. We have a sequence below, 7, 9, 11, 13, and then we see dot, dot, dot. Anytime you see dot, 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 that means that the sequence is just going on forever and it's continuing the pattern that you should already see here. So hopefully you already see a pattern. To get from 7 to 9, it looks like we added 2. To get from 9 to 11, we added 2. And we're doing that over and over. This is a sequence that's going to show up again and again in our notes today because it's a very basic one and it has a really nice pattern of just always adding 2. Of course, a sequence could be represented by a different rule, but we're going to start with this one today. So if you were to describe this sequence to somebody, how would you do it? What I'd like to do is write down in words what you might say. You would probably say, add 2 to the previous term to get the next term. Is that enough information for somebody to generate the sequence? Add 2 to the previous term to get the next term. Well, it's part of it, but you have to also tell them where to start. Start with 7. Okay, so now we can generate the whole sequence. Start with 7, and then add 2 to the previous term to get the next term. So you can even see if we were going to fill in the next term, our next term would be 13 plus 2, which would be 15 if I wanted to get the next one. So there's just an example of how you might write out a sequence and how you might just describe the pattern to somebody. But it's a little annoying to have to write down those words every time. So let's talk about the notation we would use in math class for this. The notation that we use for sequences is A sub n. And there'll be other notations you'll see out there. Some math textbooks use different notations, but just to stay consistent, this is how I'm going to denote a sequence in our class. So A sub n, or subscript n, is telling us the nth term. I realized I never even defined what that word term is, and the term is just one of the numbers in the sequence. So A sub n is the nth term. The subscript n is telling us the term number. So let's look at an example. In our specific sequence, 7, 9, 11, 13, A sub 1 is equal to 7 because our first term is 7. A sub 2 is equal to 9 because our second term is 9. A3 equals 11, A4 equals 13. The notation just lets us denote a term number and the term value. So 7 is our term value, 1 is the term number. So the first term is 7, the second term is 9, and that's going to let us kind of describe a sequence. So how do we use our notation to actually write a rule that we can read and then that'll help us generate the sequence? So we're going to talk about 2 types of rules that we could write for a sequence. The first is known as a recursive rule. A recursive rule is based on previous terms. A previous term or previous terms. Sometimes you might need more than one. So I need to know some terms beforehand, before I can tell you the next term. And the very first sentence that we wrote down in green on the first slide, that was a recursive rule, adding 2 to the previous term. How would we write that? Well, using our notation, I would like a rule to describe the nth term. I need to know, how do I just get the 16th term or the 10th term? How do I get A sub 16 or A sub 10? How do I get A sub n? Let's try to write a general rule here. Well, for our specific sequence, I know that we always added 2 to the previous term. So if I'm talking about the nth term, the term that comes right before n is n minus 1, or A sub n minus 1 is our n minus first term. Think about it. If I wanted A5, we'd need to know A4. If I wanted A10, I'd need to know A9. If I want AN, I need AN minus 1. I take AN minus 1 and I add 2. That's our recursive rule. That's the recursion. But remember, that's not enough. I need to tell you where to start. So for our recursive rule, I also must say that A1 equals 7. With these two things combined, I now have a rule, and anyone can generate my sequence. Oh, A1 is 7, and to get the nth term, take the previous term and add 2. That means A2 is A1 plus 2, which is 7 plus 2, which is 9. The third term is 9 plus 2, which is 11. So don't forget about the A1, though. We need to know our starting term. It's very important. Now, you might like this because it's pretty straightforward. You're just saying what you're doing to the previous term. But what if I asked you this question? What if I want A50? Okay, well I know A50 is A49 plus 2. What the heck is A49? Oh, okay, well A49 is A48 plus 2. You can see how this is going to get kind of annoying. With a recursive rule, it's kind of difficult to find A50, or a term value that's kind of very far off in the sequence. So the recursive rule is nice because it's a little bit easier to see and easier to generate, but it's a little bit annoying if we're trying to find a term value such as A50. Let's talk about another way to write a rule for a sequence. Our second way of writing a rule is known as an explicit rule. In this type of rule, we don't need to know necessarily the previous term. It's not based on the previous term. It's based on the term number. So for 7, 9, 11, 13, ... I'd like to come up with an expression for a sub n. And after just kind of looking at it and maybe playing around with the numbers and finding my rule, I can tell you that an is equal to 2n plus 5. How on earth did I come up with that? We're going to go more in depth later on with this type of sequence to talk about where that rule really came from. But what I'd like you to make sure of is that you can understand how to use this rule. An equals 2n plus 5. So that means that a1 must be 2 times 1 plus 5. I'm plugging in the term number. But 2 times 1 plus 5 is 7. So it works. A1 is indeed 7. Let's just check it with another one. How about A4? What do we have to get? Well, I know A4 is 13. Let's make sure our rule works. 2n plus 5, so 2 times 4 plus 5 is 8 plus 5, which is 13. So our rule works. What's neat about the explicit rule is now I can ask you for A50, and you can get this with very little difficulty. According to our explicit rule, that's 2 times 50 plus 5. So I can tell you that A50 is 105 just by plugging in our term number. So the explicit rule is sometimes a little bit harder to find, but it's very useful because it lets us find term values in the sequence that are kind of far out, like A50. If you're still stuck on how we came up with the 2n plus 5, that's okay, because we will talk about more in depth later on how we generate that rule. Let's do two last examples where I would like to find a pattern somehow. So let's look at this first example on the left, 1, 4, 9, 16. I'd like to write a rule, either recursive or explicit, that describes the sequence. So let's see, this is term 1, term 2, term 3, term 4. Can you think of a way to relate 1 and 1, 2 and 4, 3 and 9, 4 and 16? Hopefully you're realizing that 4 is 2 squared. 9 is 3 squared. 16 is 4 squared. And of course 1 is 1 squared. So our rule here for a sub n is just n squared. To get the fifth term, I would square 5. To get the sixth term, I would square 6. This is an explicit rule because I don't need to know the previous term number in order to generate that. I can just plug my term number right in. This next sequence, 5, 10, 20, 40, 80, hopefully you're realizing that to get each term, we're taking the previous term and multiplying by 2. Multiplying by 2. So that's the first thing that I notice about this sequence. So I can say that to get the nth term, I take the previous term, a n minus 1, and multiply by 2. But that doesn't let us generate the sequence just yet. I need to tell you the starting term as well, a1 equals 5. Notice I picked a recursive rule. For some sequences, the recursive rule will be much easier to find. For some sequences, the explicit rule will be much easier to find. For a lot of sequences we see, we'll be able to get both a recursive and an explicit, but sometimes one is easier than the other. So I just wanted to show an example of where the explicit rule was easier, where the recursive rule is easier. And down the road, we will see some sequences where I'm asking you to find both the explicit and the recursive. But we will generate some more formulas for that. But what's important with these sequences is being able to just recognize the pattern. Can you just kind of see what's happening before you can formalize it? Writing down the math, the explicit rule or recursive rule, that's going to take some getting used to with the notation. But just seeing the pattern is the real challenge first. So you're going to have to keep your eyes open for, are we multiplying, are we adding, are we squaring things? And there's going to be a lot of different patterns that we encounter. Good luck!